Swayam Prabha. Digital India. Educated India.
So this lecture, today's class, will look at some of the fundamental building blocks of microprocessor or microcontroller. Okay, we'll start off with combinatorial circuits or combinational design, logic design, and then we'll move on to sequential and then memory blocks and things like that in the few further classes as to go. So we'll focus on combinational logic circuits in today's class. Okay, so let me get these right. Okay, so let's see, if you talk of logic design, okay, so we'll start with some of the fundamental basics. I'm presuming here you all are aware about basic logic gates, and or nor, not, that kind of gates. Okay, so now with those gates we want to design some kind of a logic. Okay, so you want to have a solution given to a given problem, basically using some of the resources that are available with us. Okay, that is typically a design process for any design. Okay, so in the logic design specifically, what we do is, given a task, okay, we convert it into some kind of a mapping into zeros and ones. Okay, that's called encoding. And there are several different ways possible. Say you say switch is light is on is 1, light is off is your 0, like that you can have many different mappings possible. Okay, then you establish some kind of a mathematical relationship that is required based on the laws or logic that you would like to kind of incorporate into system, and then select the good design or good mathematical relationship. Okay, depending upon what are the requirements. Okay, that is typically the logic design process. Okay, so let's see simple logic that you have learned. Again, little bit revision here, but it's good to do so that we can kind of get some fundamental aspects of this logic design of the logic touched upon. Okay, so say for example AND logic you can simply implement by these two switches that you see here. So A and B, both switches are on, then the light bulb lights, and that lighting of the bulb is called as 1. Then you can have OR logic where your this circuit is put in this kind of a fashion. When A is on, A is switched on, and or B is switched on, then also your light bulb glows. Okay, so this is AND and OR logic implemented. Okay, as you can see here. Okay, A is 1, B is 1, your light is light is on. That means that is what I physically consider to be that physical mapping of physics into mathematics is 1. Okay, is what I define as 1. So switch on I define as 1, and then light on I define as 1. Then I can kind of come up with this abstract mathematical problem into a physical world problem. Okay, now the problem with this is now light is on, but now I cannot use that light on as 1 as an input to any other device. Okay, so that's where you have a problem, we cannot scale then this logic. Okay, so switches based kind of a thing we cannot scale, and that's where you see, okay, what is the element that can be used here to switch the next switch on. Okay, or that when that is 1, now I want the switch to be closed, what is this element here? And that's where people started kind of using this solenoids to do that job. Okay, and this is a way this whole area started developing into now you have multiple kind of solenoids which are kind of doing switching like this, and then some interesting things are happening in the circuit, and then there are delays related to that. There are mechanical motion inertias. A lot of these problems are there. Okay, but these problems, now you know that okay, these problems have been taken care of by design of this switching that happens in the transistors, so to say, the CMOS kind of a design. Okay, but let us look at what is this mapping typically is. From the physical world to the binary world, you can have relay logic, where your circuit is open and closed. You can have different states defined. CMOS logic, you can have zeros and ones. 0 to 1 volt is considered as a 0 state, and 2 to 3 volts is considered as state 1. Okay, transistor logic, 0 to 0.8 volts is considered as 0, and 2 to 5 volts is considered as 1. Like that, you can have multiple kind of definitions here for state 0 and state 1. These are the typically given definitions for different kinds of elements or technologies that you want to say. Okay, so now we want to design, for example, a combinational logic for a calendar kind of a problem. If this is given, how do you kind of come up with a circuit which is consisting of these gates, typically different AND gate, OR gate, or some other kind of gates, and solve this problem? What is the problem statement here? That given a month and number of given a month and a leap year flag as input. Okay, these are the two inputs, and you need to find out number of days in a month as output. Okay, so number of days in the month, we want them as a output here. So this application can be different applications, but we are just looking at this as a problem statement from the design of logic perspective. Okay, so given a month means how many months are possibility for each of the inputs. So we will have 12 months. Okay, so 12 possibilities for the input. Then a leap year flag. Okay, how many inputs can be there? There can be 2 inputs, whether it is a leap year or it is not leap year, like that. So you need to kind of find out all the all the possible inputs that could be there for the system, and then you map them onto some kind of outputs, and then you need to now define some abstract zeros and ones kind of a combination to define these months. Like say there are 12 months, so you need 12 different kind of a binary numbers to represent each month. Okay, so we can come up with many different kind of possibilities, but typically you say, okay, I'll have 4 bits used as a binary input for a month thing, so that I'll start 0000 as defined as a January month. Like that, I define in terms of these 4 bits different months. Okay, and then leap year flag can be 0 or 1. Okay, depending upon if it is a leap year, it is 1, and if it is not a leap year, it is 0. And then number of days output I can have could be possibility 28, 29, 30 and 31. 4 possibilities only exist for number of days. Okay, see look, we are not representing number here, that okay, we want 30 as a number to be represented as binary. No need. Okay, because we know that we are not having any month which will have only 2 days or 5 days. Okay, so we don't need to represent 0 to 31 as a entire spectrum of numbers as output. Okay, are you getting my point here? This is very important thing, that to see, okay, what are the distinct outputs that we are interested in. Okay, and then there are only 4 distinct outputs that we are interested in. Okay, so like that one can think about, and now one can start writing a table. Okay, a table of inputs and outputs. Okay, so how do you kind of develop that table? You put all the inputs on one side and all the outputs on the other side, and start writing their values. Okay, so input January month, okay, 0000. Okay, like that you can start. Okay, and then you see that this is typically a chart that will come. Okay, so month 0000, and then you'll have leap flag doesn't, you don't care, because whether it is a leap year or not leap year, you always have fixed number of days in January month. So for example, here they have used the 0001 as a January, okay, and this is getting represented here. Okay, so you can have your own definition. Okay, nobody prevents you to say that okay, my 0000 should be January. Okay, and then you will get this output here as 31 days as one output here. Okay, like that you can develop this kind of a table. Okay, and once this table is developed, then you can use the combinational logic circuit laws. Okay, you know that the Carnot map, or you have many different kind of ways of getting these circuits for each of the output. Okay, so for example, for this D28 output, you can use sum of the products kind of a thing, or so products of the sum kind of a thing. Like here you have a lot of options possible here. Okay, so that is how one goes about getting this combinational logic problem converted, okay, abstract problem given as a calendar problem, converted into some kind of a mathematical problem of a digital logic design. Okay, so this is what is a fundamental basis of all kind of a combinational logic design. So here the important thing to note is that there is no notion of memory here. Okay, given some kind of a combination of inputs, you'll have a combination of outputs. Okay, so whatever conditions that we are saying are not based on like okay, you have to remember something that okay, previously this was something and now it is something different. No, nothing out based on the previous thing the output is changing. No, there is no memory or notion of memory in entire of this discussion. Okay, so given this kind of fixed values here for binary inputs, you will have fixed binary outputs here. Okay, the combination of these uniquely defines your combination of outputs. Okay, so that is a kind of a way one can design. So see, now here you can see that okay, D28, these are 4 kind of outputs. I could have converted this problem into just 2 outputs as also, because 2 binary numbers I can represent 4 different combinations, 00, 01, 10 and 11. Okay, so I can say my 00, if it is output, then it is 28 months, 28 days in the month. Okay, or 01 is output, 29 days in a month, like that I can say, and then this output could have been reduced. Okay, and that would have saved me some circuits. Okay, like that one can kind of think about. So we will not get into the details about how do we do the saving, or how do we kind of develop the circuits which are optimized. No, we are not getting into all that here. Here our basic idea is to understand these fundamentals, how these different combination logics are developed. Okay, and like that there are now one can use this this is sum of products kind of a rule that I have used here to get for the output for D28. Okay, and then it's in the combination of and not kind of gates. Okay, so like that you get all these things developed here, and you finally express everything as some kind of a logic expressions. Okay, and in these logic expressions can be converted into a circuit. Okay, you can convert them into a circuit by before simplification. After simplification is all you have a lot of leeway to play there. You can use Carnot maps or De Morgan's law to simplify things and get to some kind of a desired output in the desired form actually. Okay, so these are different circuits that are for different outputs here. Okay, so now there are these kind of questions you can ponder over. Okay, you can see these questions and ponder over them, and think about what could be the answer for such a question. Okay, and then this is a say D30 output circuit for D30 output and things like that. Okay, so like that you can start developing now these kind of logic expressions and logic circuits for many different kind of combinational logic elements. Okay, so we'll see some of them, but I'm going to go a little faster through that, so that the idea is to you can pause at any point of time and then go through these examples, solve them on pen and paper, and then look at the solution. That will help you internalize the concepts very well. Okay, but I'm going to go a little faster to kind of because fundamentally there is nothing different there. Okay, all are in this kind of a combination of some kind of a solutions here, that the once you know this process, that okay, you express each of the outputs okay in the form of these inputs by using the sum of the products kind of a rule, or some other kind of a rule, depending upon what the problem gives a simplification to. Then one can kind of start developing this first expression, and then use some kind of a digital circuit laws to simplify this in more details. Okay, so that is what is I'm leaving it for you to kind of learn yourself and develop that. Okay, by the way, even if you don't know how to simplify and how to kind of get some circuits, is okay. There is it's not a requirement for understanding microprocessors. See, it's like when you start using computer, you don't know what is inside, how it is really processing everything, but you can still use computer and write your codes in say C language. Okay, so C language you learn, and you don't worry about how it really processes things of each of the C language command inside. Okay, it's like that. Okay, so even if you don't know okay how these circuits are doing their job, it's enough to know that okay, by using some kind of a rule like this, or some kind of a circuits like this, your output can be produced. So that is what is most important kind of understanding here. So the way this calendar example is done, now we'll see say some addition application if you want to do. So half adder and full adders are which are useful in arithmetic logic unit in the microprocessor. Then multiplexers you can develop. Okay, they are useful in developing multiple channel interfaces for analog to digital conversion. That is one of the interface for microcontroller microprocessor. Then comparators, again useful in arithmetic logic units. So these are some few kind of examples only which we have taken, but there are many different kinds of these circuits that can be possible, and one can do lot of operations, say logical operations, and these addition operations, comparison operations, like that. Those all operations can be done by using these combinational logic circuits. Okay, so these are at the heart of all these microprocessors, particularly arithmetic logic unit in microprocessor. And you have this 7-segment display, one of the examples we have, which is an output device where this 7 segments will give you some kind of a representation of a number to display to a user. So if you are aware about these devices already, you don't need to kind of go through this part already. Okay, so you just, because this is just a same kind of application of our combination logic fundamentals. Okay, so we say for example now this half adder. Okay, so there are these two numbers A and B, binary numbers, when we want to add together, and then it should have a carry. Okay, so what is the expression for carry and sum? Okay, so if A is 0, B is 0, my carry is 0 and sum is 0. If A is so like that, you fill out this table. Okay, you pause here and fill out, and then again see that. Okay, it will be like this. And then for implementing this, you can find out this Boolean expression, and once you get this Boolean expression, you can get corresponding circuit related to that. Okay, So there is a XOR gate coming up here. Then like that you can have a full adder. Okay, so you have a carry in also now. Okay, so A, B and carry in also is there, so that you can now multiplex it and get more of these going. Okay, so then you go ahead with the same process for these. Now you have 3 inputs, and now you see what are your outputs. So again pause here and then proceed. You will get these as outputs, and then you can find out corresponding expressions for that, and then those expressions can be converted into circuits by using AND gates and OR gates and NOT gates and things like that. Okay, or XOR gates and things like that. Okay, so like that, this is a implementation, one of the implementations of the adder. Then this is another kind of a expression where you don't want to use XOR gate. So you have to have some simplifications done to get to these points and things like that. Okay, so you have this circuit coming up, exactly the same kind of implementation carried out by this circuit also and the previous circuit also, but now there are some kind of other simplifications. In particularly here there are no XOR gates in this case. Okay, so like that you can have some conditions put and find out circuits satisfying those conditions. So there is a levels of implementation that will also be another kind of a constraint that can come in. Okay, so so we'll not get again into details of these, but one can go into these different kinds of aspect. So these are the third implementation of the full adder kind of circuit. So there are some kind of fundamental thumb rules for implementation of the circuits coming up mainly from the circuit design perspective, which we are not too much interested in getting there, because we just that okay, full adder works like this is sufficient for us to know. Then you have a multiplexer. Okay, so multiplexer has this input 0 and input 1. Okay, so 2 data inputs are there as IO and Y, and control input is A. Depending upon value of A, the one of the inputs is selected here. Okay, so you can see that this condition, like okay, say for example IO is 0 and this one is also 0, and value of A is 0 or 1. Depending upon that, if A is 0, I will select I0 as a Z, and if A is 1, I will select I1 as a Z. Okay, so like that circuit will come up here. Okay, so you fill up the entire table and then we will proceed. So you will see this table something like this. Okay, so when A is 0, it is selecting this input, A is 1, it is selecting this input. Okay, so these inputs are like, these two cases could be possible where input is same. Okay, IO and I1 has some values which are same, but A is different. Okay, so A is 0, it will select I think this is different either. So depending upon A select, so A is 0, it should select IO or I1, depend upon, like, we will see what is getting selected here. Okay, so here A is 0, it is selecting I1 here, and A is 1, it is selecting this here. So here again same thing. Yeah, so A is 0, it is selecting I1, A is 1, it is selecting I0. Okay, so like that. So doesn't matter, you can have your own way of having this also, but this is one particular kind of a definition, like depending upon A, you are selecting the output, and then you can directly write in terms of Z is I0 or I1, so you can write it like this also directly. So this implementation of this is again you can convert this into a circuit. Okay, and you can have scaling of these multiplexers possible. Okay, so 4:1 multiplexer is you have 4 inputs, and one output is there. Okay, and out of these 4, one will be selected depending upon the select pins. Okay, the select pins are inputs. So now to have 4 inputs, one of the 4 inputs selected, you need to have 2 select pins, and then you'll have corresponding expression for Z. Okay, and this will not worry about this. So think about this other problem. This is a separate problem, that you can use multiplexer instead of your AND or gates for implementation of some of the logic circuits or logic tables. Okay, so this is a way the multiplexer can be implemented. Then you can give this I0, I1, I2, these are the inputs that are coming, and then these are the select pins, and depending upon the select pins you can have multiplexer implementation. The Z output is coming. Okay, so like that you can have many different other examples. Okay, so maybe you can go through these lectures yourself. Go through these slides yourself. This is the same kind of a process we are repeating over and over again. Okay. So in the similar way you can have definition of comparator. Okay, so you want to compare 2 numbers which are represented by one number is AB and other number is CD. Okay, so AB are like 2 binary kind of bits of one number AB, and bits of the other number are C and D. Okay, and then you need to kind of give the output. If it is less and if it is more, you can have some kind of outputs that are possible. So you can think of this implement the truth table for this will come up something like that. Okay, so A, B and C, D, they are equal, then this will be 1. If they are less, if they are more, that will be 1. Like that it will have these 3 inputs coming out 3 outputs coming out of this circuit. Okay, given based on these 2 or 4 inputs in terms of bits. And then you will get this entire table represented, and then you can find out further how its circuit could be. Now there are these other kind of output elements called 7-segment display. Okay, this is very important for mechatronics people. Okay, because a lot of these displays can be programmed with this understanding of the 7-segment display. This is nothing, this is just a combinational kind of a logic here. Okay, and you want to display say 1 here, you need to see, okay, what are the these elements of this display to be these are basically LEDs, they should be lightened up. Okay, to display 1 or 0 or whatever value you want to display here. Depending upon that, you will have multiple outputs, and then you can have additional problem saying that, okay, oh, look, my binary number needs to be getting represented here. Okay, 8 binary numbers or 10 binary numbers from 0 to 9 should get displayed here, starting from 0000 to 1001. Okay, they need to get displayed here in appropriate kind of a fashion. Then how do I kind of program this circuit which can do that. Okay, so this is BCD to 7-segment control decoder kind of circuit that we can design by considering this logic table. Now we can fill up this logic table, and again the same process is to be carried out, and one can get big circuits to kind of implement this logic. Okay, and then these are different kinds of circuits that are possible, and they are done in the as a basic kind of circuits for these different elements, and then these elements now can be further put together to create your entire microprocessor. Okay, so this is, for example, you want to display 2, you want this LED and this LED, this LED, this LED and this LED to glow. So that is what is given here. Okay, so 2 is 1 0 representation in binary, A B C D 4 numbers are represented like that, and then your corresponding this 7-segment display LEDs are glowing, they are said as 1, and then you can get this number coming up there. Okay, so so like that you can fill up entire table in the similar kind of a fashion, and once this table is filled up, then you can look at one output here, and in terms of 4 inputs, like what combinational circuit will come up is what you can consider. So one can do that. I mean, that's very what do you say, simple but tedious kind of a job when we go for this kind of a big circuits, multiple such elements. Okay, so these are the big expressions that are coming up here, for example. Okay, so now we will stop here for now, and we'll take up in the next class these sequential circuits. Okay.